Okay, so you've got these two scenarios, the main scenarios that people discuss, and it's not the whole story, but there are textbooks written about this difference. We brought up the Sugimoto situation here, this broadening, the change in radius with time of the solution versus a critical concentration, which is like a reference concentration that is related to the size of the crystals of the solution. Okay? That critical concentration is an equilibrium concentration for a given radius. And if you're higher than that, so supersaturated relative to the particle that you're considering, you can get into a, and you're under diffusion limited conditions, then you'll get into a size distribution narrowing situation. And beneath that, for instance, let's say you're at, at critical concentration or below, the distribution will actually broaden. And so Oswald ripening, we mentioned, is one of these processes where you're at equilibrium in the Lemire diagram, you supersaturate, you nucleate, you grow, you come back to the bulk solubility again, right? No longer supersaturated, and the distribution will ripen, and you'll get broadening of the distribution of those conditions. All right, so we also introduced this thing that I refer to as kind of like the mass balance model of nucleation. There are three legs to this process. There's the precursor conversion part of the reaction, leading to solutes that then can lead to new crystallites or can attach to existing crystallites. And these three legs all have different rates, and depending upon those relative rates, you get different sizes and you get different size distributions. And I've shown here for the nucleation process, the classical expression for the rate of nucleation versus the supersaturation. Here I've shown an attachment and the growth mechanism, but you can have a diffusive limited one here. And then there's the rate constant for the conversion step. And it's the balance of those things that matters. We talked about how the rate of the production of this stuff can dictate the number of times this happens. Right? The number of nucleation events is related to how quickly solutes are produced and how quickly they're consumed. Okay? The more time the solutes sit in solution before they're consumed, they have this chance to nucleate. If there are many crystallites or crystallites grow quickly, this lag of the reaction competes with this one effectively. Don't make very many crystals, you just grow them. Okay, so the number of crystallites you produce is related to the rate of the consumption. It's inversely proportional to that rate of consumption in this picture. All right, so we're going to talk more about precursor conversion and also these growth steps today. And I wanted to show a class of precursors that my group has developed here. Did I mention these ureas and urea compounds last time? Yeah. Okay. So these compounds are starting materials that are used to make metal chalcogenides, and they're really powerful because of the relative rates of their conversion reactivity. You get about a factor of 1 billion. It's probably more than that, depending upon what the substituents are, which makes them useful at a variety of temperatures and the typical reactants and so on. So when you use these sorts of compounds to make particles, there's examples here, one of the early ones from my group, showing the reaction of the thiourea with lead oleate to make lead sulfide. You get different kinetics of the conversion reaction. Okay? These are conditions where the breakdown is the slow step in the process. The previous graph I showed the conversion reaction being slower than the consumption. That's what you're observing here. And so the kinetics of each one of these curves, where you have a different substituent on this phenyl group here, these are the lead sulfide yield kinetics, the total amount of lead sulfide being produced in the solution, and the differences between those are entirely dictated by the breakdown of this compound solution. So there's all this nucleation growth stuff happening. All you see is the decomposition of this thing, because decomposition is great
in this process.
all the other steps happen fast relative to that. So you can then fit these curves, pull out rate constants, and those rate constants are related to this breakdown. If you're familiar with Hammett plots, which you ought to be, here's a Hammett plot for these various constituents, and
It basically says that electron deficient compounds are faster than electron rich ones.
you can use that to speculate
About the breakdown mechanism like that. You can also say all of these compounds likely break down by the same type of mechanism because there's a systematic change
in the reactivity with the substituent pattern according to this Hammett relationship. So they're behaving themselves, is another way to say it. So the reactivity, these curves, all dictated by the breakdown of this compound. And then, of course, the thing we mentioned was the rate of that breakdown turns out to be related to how many crystals nucleate. So when you have more reactive compounds, you nucleate more crystallites. Sugimoto's mass balance equation predicts this kind of thing. Faster kinetics means more time spent during nucleation. It takes longer to reach a number of crystallites sufficient to consume all of the solutes and drive the concentration down. So, so this approach to doing synthesis turns out to be really valuable because you can run reactions under otherwise identical conditions, temperature and concentrations and whatever, and just pick a different compound, run the reaction to completion, and pull out a different size of the reaction. This is very different than other approaches where you might stop the reaction early and throw away a bunch of starting material, having to separate it from the products. Being able to dictate the number by controlling the reactivity gives you independent control over the size and allows you to simplify product mixtures. Di-substituted thioureas are about as reactive as tri-substituted ureas. Remember, the number of substituents increasing slows down the reactivity. Carbon-selenium bonds weaker than carbon-sulfur bonds. And so these compounds are more reactive to these compounds inherently. So anyway, you can do that with both lead sulfide and lead selenide. Now, we've also, my group's demonstrated this in a variety of materials: cad sulfide, zinc sulfide, cad selenide, the lead salts, zinc, I already said zinc, indium phosphide. So this is a pretty common feature of nanoparticle synthesis in general. All right, so I'm going to talk to you about how we monitor these reactions today. And X-ray scattering, these uses principles used there, and how we can use that as a row. So typically, when looking at these reactions, you know, the sort of old school way is to go in there and pull out a sample. Remember the video, the guy taking off putting in the vials and diluting using salivation. You can take spectrum those points and do kinetics that way. Or you can take your reaction and put it in front of an optical fiber and record an absorbance with time in situ. Or you can take the flask to the synchrotron and do X-ray scattering experiments on the solution as it's growing. And this is a much more potent way of looking at the system because it's faster. It also is a more objective measure of size. So I'm going to talk about these two techniques here. So you're probably familiar with the Bragg condition in an X-ray scattering or diffraction experiment. You have X-rays coming into a crystal, and they get reflected off of the planes of atoms. And what ends up happening is that these two X-rays come in, bounce off these two planes, and this one travels a little longer distance than this one does. That also travels a longer distance. And when the wavelength of the X-ray is on the order of the distance that's traveled, the X-ray distance that's traveled, you get interference effects.
effects give you scatter patterns you can fit to determine things like this D spacing here. The D spacing in these planes are related to the rate and the angle of the scattering.
So, constructive interference
and destructive interference is an absence of signal,
and you can interpret that
and measure separations. This works well when the wavelength of the X-ray or the photon
coming in is the same
is the space. Why would X-ray scattering
to determine the structure.
visible scattering can give you
Macroscopic structure, same sorts of principles. So when you have crystallites in solution, you know, you get an X-ray pattern at the day. It's got some peaks present here. Like here's this one's labeled the 1, 0, 0. That's because that's the direction of the distance being measured. Here's a second harmonic of that, the 2, 0, 0 direction. It's just sort of two planes being separated from each other. There we go. So when you have many different crystallites in a sample, like the one shown here, you've got different orientations of the crystal producing a reflection, and the sum of all of those will give you the complete pattern. In this example here, not all of the planes are aligned in a way to give scattering at that particular separation. Whereas in this example, you have many different crystallites. All of them will diffract, and you get peaks characteristic of all various size spacings present in this sample. Okay, so this powder X-ray diffraction pattern is used as kind of a fingerprint of an X-ray structure. And you can go look up these patterns. You know, most substances have been made. And so there are libraries of these kind of things. And you can just go and say, hey, I've got cadmium chloride in my sample because I see its characteristic reflections. Now, in a single crystal X-ray diffraction, you put your specimen inside of this X-ray beam. It scatters in all directions. And they talk about something called an Ewald sphere. So that's sort of all scattering directions off of the sample. When you have a single crystal, what you see are these patterns here. This is probably where the beam stop there. You get this wonderful pattern showing the orientation of all the directions in the crystal lattice, and you measure all these intensities, and from that you can determine X-ray structure. In a powder, instead of this spot pattern, you basically get a ring pattern because of all the possible orientations of those crystals, and those rings, if you actively integrate them, give you these peaks that we saw on the previous page. Anyway, that's the connection between single crystal and a powder pattern. Now, it turns out that the X-ray, so here's a series of example powder X-ray diffraction patterns for cadmium selenide quantum dots. I'm very familiar with these, so I can tell you that this pattern corresponds to the Wurtzite structure. And you can see all the peaks for the Wurtzite crystal structure labeled up here. The various directions in the lattice. And what you'll notice in this series of patterns is that the width of the peaks that you see here is changing. So down here at the small end of the spectrum, you'll see very broad signals, and as the crystallites get larger, the peaks sharpen. This is a very well-known phenomenon. People will use this to model the crystallite size. So there's a pretty well-defined relationship between the width of the peak and the size. The sort of lowest tech version of this modeling uses the Debye-Scherrer formula, relating size to the broadening that's present here and the angle in which you're measuring. So you go to the allowed size in a sort of simple fashion. You have to be very careful when you do this type of thing because strain and defects can also be present broadly. And PPR is also limited by the
Okay, so it's not right here, you need to know the broadening associated with to get this value appropriately. So there's a lot of things that can contribute to that breadth. It's not totally straightforward, but it's pretty straightforward to look at this and see, 9 nanometers out here, there's still a fair amount of broadening in that pattern. This is the size range people are mostly interested in. So you can look at an X-ray pattern and size up your crystals just to the background this way. So this is one of the ways to monitor crystal growth. Just a side note here, when you're doing single crystal, people talk about the angle of reflection. People who do scattering for a living tend to talk about Q rather than theta. Q is another measure of the angle of scattering that removes the X-ray wavelength from the equation. Okay, so if you work with synchrotrons and fancy experiments, you do neutron scattering, like electron scattering, the wavelength is no longer just might be a whole bunch of other stuff. And to make it easier to look at patterns and to calculate things, you just apply this relationship between theta and Q. But for the sake of discussion, these two things are sort of equivalent when you consider that wavelength. So here's an example of X-ray refraction pattern taken at a synchrotron. This is a lovely looking pattern. Look at all the rings that you see here. This was collected on a detector that's probably about this big. It costs a couple $1 million. This is a very high-end X-ray scattering pattern. And it turns out you can take these patterns and Fourier transform them to produce things called X-ray pair distribution functions. Okay, so we use X-ray pair distribution functions all the time in the group because they tell you about the structure of the solid with more detail than you get just by looking at this first pattern. This is an X-ray refraction pattern of methyl lead iodide, and all these peaks are related to the size of the crystallites and the crystal structure. I'll show the slide on that in just a moment. But to do this type of thing, you need very high energy. To do this well, you need very high energy X-rays. So this is not typically done on a normal lab source, although you can. And I would love to get a diffractometer here in chemistry or those types of things. Usually you need like a special X-ray source to get, the higher the better, brighter the better. And you detect X-rays over a very wide range of angles. In fact, in the single crystal X-ray experiment, you go look at the peaks, how far out the peaks, how the X-ray structure is. A lot of really interesting information, useful information in the PDF pattern occurs out here where you don't really see a lot of intensity, but there is still a lot of scattering going on. So you need really wide angles with high counts. You do this type of thing well. So typically on this this pattern, this pattern is really taken around with interatomic distances. Yeah. This is a probability. GFR is expressed a bunch of different ways, but it's it tells you about the probability of having scattering from a given distance relative to the average scattering of the sample. Okay, and it's also corrected for there's something called scattering factor that's used in this. That's related to the material. That's scattering. I don't know how much of an impact that really has on the final shape or how but you notice how some of the signals here is like negative, and that's because you're very unlikely to get scattering at this particular distance. You're relative to the average scattering of the material. The thing you really need to be paying attention to in these patterns is just the shape and intensity of that. Okay, so this is a history of instances in the solid.
When you see a peak, it's because
you have two sensors of electron intensity. Electrons are scattering X-rays. It's very likely that you're going to find electron densities 3 angstrom apart from each other in this sample. And so you can see here how this pattern is labeled with this 2D material, boron nitride or whatever it is, all relative to this atom. Right? So what we're looking for are regular distances relative to this atom in this structure. And you can see the nearest neighbor distance here corresponds to the first peak in the pattern. This is the second nearest neighbor. That's the second peak. There's a third nearest neighbor. It's not labeled with the ring, but that's its peak there. Okay? There's the fourth nearest neighbor. And so you get these peaks that tell you about regular separations. You can do this on a gas if you want. You can measure the distribution of this distance in gas. You can do this on liquid water and measure the oxygen separation water in the second neighbor. And we'll tell you about the coherence of the material. How regular are the spaces? Okay, so like so in this pattern, notice how the peak intensity decays. Right? And peaks get broader, and that's because 5 nanometers away, there are no more regular correlations in the substance. And that tells you that crystallinity in this material is limited to 5 nanometers or less. Now, if maybe you don't have any crystallinity, it's just water, right? Water is going to have some coherence up to maybe the second or third nearest neighbor water molecule, and then all the vibrations and clusters that tend to happen start to fall apart. There's no more regular separations beyond a couple of water molecules. Okay, so the pattern's regularity tells you about how ordered the material is. And that's really powerful when you're trying to say, structured solids and liquids, polymers. Okay? So this is really fancy pants stuff, and it's becoming more and more common to use it. It is incredibly powerful. Here's actually one of our reactions at Brookhaven Synchrotron, where we run our nanoparticle syntheses this way and pump the solution in front of the beam, and there's that multi-million-dollar PDF detector waiting to collect all of those, that wide range of angles. All right. One more scattering technique that people use is small angle X-ray scattering. Here, notice the y-axis is Q, so this is like angle, right? Normalized by the wavelength, and it's a log of Q. Here's the intensity of the scattering versus angle. Both of these are all plots. And small angle X-ray scattering, right? The angle of the diffraction or the reflection is diffraction is related to the separation of things that you're measuring. So you have very small separations. You get very wide angle scattering. When you have large separations, you get low angle scattering. So if you want to study things that are, if you want to study large objects, like let's say a particle or a region of a polymer, and how ordered it is, take a look at the small angle X-ray scattering, and you get these patterns like this, or something like a sphere. These are various calculated small angle scattering patterns for spheres, and people talk about 2 regions of these, what's called the Poirot region and the Meunier region. The size of this region here is related to the size of the object of interest. So before it sort of turns into the Poirot region, the width of that is the radius of the thing you're studying. And then the slope of this line, or the slope of the intensity and type oscillation that you see here, tells you about the size and also the polymers. So here's 2 different spheres scattering radius of 10 nanometers and 1 nanometer. You can see the 10 nanometer thing. The Meunier region is larger, So it sort of
decays at a wider value of Q than something that is larger. The larger one has the smaller angle, just what you'd expect. And then the slope of this thing, Q to the minus fourth, is related to the shape. And then there are these sort of dips and regular oscillations here. For a perfect sphere, these dips go all the way down to the baseline, I think. Nearly so. In a real sample, there's polydispersity. That's what the sigma value is here. When you don't have all the same size, you get a bunch of these slight oscillations and put them on top of each other, and you get something that looks like the blue line or the green line. So the width of these dips allows you to extract polydispersity. So the first time I saw patterns, I was confused about all this stuff. I'm really intuitive of what log scale of intensities is Q, and know that spherical scatters have this, rods have another shape, platelets have another shape, and you can model these lines to extract shape and size and polydispersity. You can have an ideal sample. So nanoparticles of the type that people may think in photosynthesis, they are sort of idealized, and you can get a lot of information about them by modeling that shape. So if you take X-ray PDF patterns as a function of time, there's electric data as crystals are growing, and you can see at early times, the patterns are kind of broad and they're not long-range coherences. And as the crystals get larger, you see this spiky pattern here. This spiky pattern is characteristic of a rock salt crystal structure, and it decays around 40 angstroms or something like that. These are 4 to 5 nanometers. Calculate what these patterns look like for a given size shape, trying to fit in these scattering patterns from that monitor crystal size. You can also take X-ray small X-ray pattern, there's a real small angle pattern from crystals grown by our group. And you see a nice image of it gets flat, it's flat out here to show that you have small objects that will divide from each other. And then out here in the lower region, you get these oscillations. And so fitting this stuff will tell you about the size of this region. And the total amount of scattering will tell you the intensity. So you can use real quantitative measurements this way of size, polydispersity, yield by modeling patterns of this kind. So all of these are great ways to study crystal growth. Here's an example data set. Look at here how the oscillations are kind of moving from wider angles to lower angles. And I haven't drawn a line in here, but this is a wider angle than that. And it tells you crystals are getting larger with time. The depth of the oscillation is getting more pronounced with time. And from these patterns, you can fit the radius or the polydispersity. So very clean looking kinetics. Here, not perfect fit with these wider angles, but not too bad. Here's the same experiment, but now being monitored at wide angles. Okay, so this is, notice Q of 10 to 40, and here's Q of 1. So small and wide, and get the characteristic reflections of a rock salt crystal structure. They're labeled there for you. You can see in the beginning, the peaks are broader than they are at the end, and then you can take that intensity here and plot it versus time to measure yield, and you can take the width of the peak to measure size and polydispersity, turns out. All right, so here's an example of data now where we've taken all of these curves. Again, they're getting larger. So this for a region is sort of, the Gunier region is shrinking. And then fit each of those wiggles to extract the radius of our particle time. And then because we know the intensity is related to the yield and we know the radius, we calculate how many crystals are present in the solution at any given time. The total amount of stuff divided by stuff per crystal will give you the amount of crystals. And so these experiments make it possible to see an increasing number of crystals with time, which is a measure of crystal nucleation. So, with really good scattering, high intensity X-rays, and fast electronics, you can take one of these patterns every second or more. The European synchrotron in Grenoble is the fastest of this type of thing. Out here at NSLS2, which is also very good for these kinds of measurements. These patterns come off in, a couple of seconds, maybe in 10, 20 seconds or something like that. Still very fast. I should say, we're doing experiments with lead because lead is an extremely good scatterer of X-rays. The scattering probability is relatively electron density, so it goes with the Z squared. Okay? And so the heavy elements much more effectively scatter the electrons. And then let's just basically the best case scenario is one of the heavy elements in the periodic table. And so they're perfect type of measurements. And that's part of the reason why it's possible to collect patterns with high frequencies. All right, so this is a rare example of nucleation kinetics being monitored directly. And what you'll see actually is that in this particular experiment, it takes about half of the reaction before nucleation stops. Okay, so we spent a lot of time talking about how the polydispersity in the synthesis is related to the width of the time that the nucleation process happens. And in this experiment, it's half of the reaction. You see the number of nanocrystals increasing. Okay, and so this measurement clearly says that there is no burst of nucleation under these conditions. But nucleation happens very slowly and continuously. This data set is about to be published. It's being reviewed. We're going to submit our second revision on this paper. But this data is actually about 6 years old now. The first time I saw it, I thought, there's something wrong. The experiment kind of failed because it doesn't match the temperature. And since then, we've shown a variety of different needs that this slow nucleation thing is actually pretty common. All right, so in these same experiments, we actually went about measuring the conversion kinetics independently. So Brendan McMurtry, who just graduated, made carbon-13 labeled ureas and monitored their decomposition to this N-oleoyl urea byproduct. You can see that in C13 mass spectrum here. There's the urea in A, there's an N-oleoyl urea product here. And so these kinetics give us a direct measure of the cellular production. And so now we have that's what's plotted here. It's the conversion activity expressed as a yield of lead sulfide units. So the appearance of lead sulfide is plotted here, but it's not measured by that. It's measured by the decomposition of that. And then the black solid trace is the X-ray scattering that we measured under these same conditions. And you can see that the yield of lead sulfide, the appearance of crystals, and the disappearance of the precursors do not match each other. It takes some time for the crystals to appear after the precursors are converted. So the amount of solid, the number of units that are missing here is actually the solid one here. If you think about this experiment, what we're measuring is concentration of solid material using the X-ray scattering curves. And we're also measuring the amount of precursors that have converted. And the difference between those is something that is solid. This lead sulfide formed by conversion that has not yet precipitated and formed an nanoparticle. So we can calculate those solid curves and that's shown there as solid. So in these reactions, we have slow nucleation. The solute concentrations reach very high levels. So this is all lead sulfide
at the other reaction here, you can see the solutes, about half of it, a third to a half of all of the lead sulfide is not in particles and not in precursors in one of these reactions. And it's very linear-like in the sense that the solute concentration goes up and then it decays as it approaches equilibrium. What's not linear-like is the nucleation phase being short. We have, well, let me just say before I show you all of that stuff. The central question that I've been leading with here is what controls the polydispersity and the size of these reactions. It's about size being related to growth kinetics and solute production kinetics. Faster solute production gives you more particles in a smaller size. Faster growth consumes solute more effectively and reduces the number of particles that you get. Polydispersity, however, we said, well, maybe it's this burst of nucleation thing. Clearly, it's not in these reactions. These reactions produce ensembles that are so narrow, it's hard to measure their polydispersity. And yet they are these additions of reagents very slow. So the issue is, how do you explain polydispersity then? And what would you say the answer is to that question? Somebody not in my group, please. How do you explain the polydispersity if the nucleation is so long? Let's say you go to a horse race, and you want to answer?
Is it something about how it is started? Not the one that started at the beginning, that like you created and then it's like probably growing and you have more nucleation starting.
Yeah. So how do they end up the same size as these really?
Or like maybe.
It's a good guess.
Isn't it that bigger? It's broken back down.
Yeah, so that's possible explanation. There's a thermodynamic driving force to the right. Everything I've talked so far suggests that's not true. I think that is true in this condition. Like we were trying to make a cluster, for example, the ligands make the clusters all the same size because there's a particular ligand arrangement that is desirable. These are much larger. So you don't have a simple preferred size. We taught you one other mechanism for giving for producing narrow dispersions. You know the answer to this already. Yeah. Right. The smaller ones grow faster than the bigger ones do. But it's not organic. It's organic. That's one organic reason that you could provide. Yeah, so diffusion limited growth gives you distribution narrow, right? It turns out these reactions are total effect, they're very sensitive to the diffuse acidity. And so the way that we measure this is by running these reactions with different alkane solvents. Octane icosane is C20, this is C8. And the viscosity changes by a factor of 4 or something like that. And you can see that the number of nanocrystals that you produce is sensitive to this. Right? So when you go to a more viscous solvent, the number of nanoparticles drops. So why does that happen?
The number of nanoparticles is related to two things that we've talked about so far, right? One is the precursor conversion reaction, where you have fast solid light nucleating more particles because the nucleation takes a longer period of time. You need more particles to consume all of that flux of solutes and drive the concentration down. The other thing that dictates the size of the precursor conversion reactivity is under the mass concentration number to the slide rate over the what's another way to drive the concentration down? Change the growth rate. So if the crystals consume solutes very well, if the growth rate is fast, that helps hold the solute concentration down to nucleation process. So if the growth rate is fast, you don't need to burn the crystals. One crystal will do it. So all the solute in the solution, no other crystals have a chance to form. So the size here, the number of crystals, is telling you about either the precursor conversion kinetics or the crystal growth kinetics. And what would you expect to happen if you make the solvent more viscous? Should the growth go down or go up? Growth should go up if the solvent more viscous. Down? Why down? Yeah, we're talking about diffusivity now, right? So if you make the solution more viscous, the diffusivity will drop. If the growth rate is slower, what should that do to the number of particles? Yeah, if the growth rate is slower, the crystals don't grow, and all the solids will nucleate instead. So a slower growth rate means greater number of particles. That's not what we see here. So diffusivity is changed by a factor of 4, the nanoparticle concentration should go up. And in fact, it's going down. The reactivity is also slightly going down. So here is that solvent. Here is changing the conversion kinetics slightly. And that may be the explanation for why the nanoparticle concentration is dropping. What doesn't happen, it doesn't go way up. It should if diffusive kinetics matter. And they don't. That's the point of this data. So diffusivity is not meaningfully impacting growth kinetics. Our particles, and that tells you this is not diffusion. Yeah.
So that's good. This is
Correct.
Yeah.
I'm not sure entirely how people study this issue on other systems. I think things like stirring matter, mixing, influence the depletion that occurs around the surface. So stirring effects can be used to make a statement about if this is sort of those conditions. I don't know how, if you use it really small, then it's about that. But this is another way to approach it. All right, so I have shown you now that diffusivity does not matter. So I'm not going to get into this, but it turns out you can relate the polyphoreticity sample and you can basically model these curves to extract a size, a growth rate on a per particle basis, function size. And so this modeling allows you to see that there are conditions, you have a broad distribution, you'll get size distribution focusing. And you need that to explain the polyphoreticity, like I said, right? The nucleation is really slow. They all turn out the same size at the end. You have to have this
narrowing. The best sort of simplest fits are for radius dependence about
harder than minus 1.5, but it could be higher than that actually. All right, so it's not diffusivity. So we have this problem, you know, the horses are being let out of the gate slowly, and they run around the track, but eventually they stop running, and the smaller horses catch up. Okay, and then not on diffusion growth, it's frontal loss. Okay, and it turns out that's something else that is associated with the attachment of the monomers to the growing crystal. So, but the picture that I might just put forward is that, and we're not the only ones, that the polysurface comes from differences in the reactivity of small crystals and large crystals toward growth. So smaller crystals grow rapidly than large crystals do, for some reason that is unknown. But that doesn't you don't diffuse the growth, and you don't lose them. So that's cutting edge nanoparticle polydispersity control for you. Let's see here. So maybe a couple more observations. Temperature is a very interesting variable in these reactions, which we've studied. It's hard to get a synchrotron time to do experiments of that kind, that they're the sort of most definitive measure of these kinds of kinetics. But you can also do them by taking aliquot. So here's a collection of absorption spectra. Throughout the infrared, we're looking at that sulfide. You get these nice peaks, and you know the shift in peak tells you the particle size is increasing. The absorbance of the solution is increasing. The increased absorbance means more of that sulfide, and you can take these peaks, their intensity, their width, and position in the spectrum, and extract the radius and the yield, and that will allow you to calculate the energy concentration, which is shown here in pink. So this is much like the X-ray scattering curve now, measured using the solid method, or watching the concentration increase and then reach a maximum. The black points are the yield of lead sulfide, which is a peak intensity, essentially. The extinction coefficient is size dependent, so you have to have a relationship showing how the extinction changes with size to do this type of measure. Okay, so we've shown nucleation is slow with diffraction or with scattering, but we can also show it using absorption spectroscopy. I'm not going to explain that. It turns out if you change the temperature of these reactions, the influence of temperature is multifold. I thought I had another slide stuck in here. Maybe let me just jump ahead or go back and look for it again. Let's jump. We can take it here. It's the same one we've talked about in the past. So when you change the temperature of a reaction, you can influence all of these different processes. Okay. So say if I run my crystallization at a higher temperature, what do I expect to happen? To really understand that, you have to look at temperature to influence these two steps. Right? You can't just look at it in one isolation. And the main thing that you should do is a rate determinant process. Even if this rate determinant these will have different temperatures. It's not really clear, what should happen. Look at the classes of nucleation expression. You have this critical concentration behavior. Where area is defined by the thermodynamics of the critical radius. You get this needed six type of relationship. So super temperature sensitive. The attachment mechanism, the radius behavior is going to be temperature, and the solubility is also temperature. So all of these things are going to have temperature dependence that can influence the reaction. So let's take a look at what happens here. So now I've plotted for you, we're looking at the size of the crystals here. This is also size, so there's diameter scale. There's a scale in terms of the volume of the crystal expressed as units here of lead selenide in this particular data. And what's Q? Q naught is the initial rate of solute production. This is Sugimoto's measurement. So if you have fast solute supply kinetics, you should get a greater number of crystallites. Fast precursor conversion gives you a higher number, and that means a smaller size. Okay, so as you go to the right, here's a log scale for indium phosphide, a linear scale for lead selenide. As you go to the right, you can see these purple points here going down, the blue points going down, the green points going down. It's hard to see when things are so small, but basically the faster the reaction, the smaller the crystal you produce, and the same is true here for indium phosphide. The faster the reaction, the smaller the crystal. Temperature is plotted as a color. So if you go to higher temperatures, what you find is you make larger crystallites. Okay? You want to make something that's 7 nanometers, you need to be up around 250 degrees. If you want to make something that's 4 or 5 nanometers, you need to be down below 200 degrees. Okay? Same is true for lead selenide. If you want a big crystallite, you really need to be at high temperature. If you want a small crystallite, you want to be at low temperature. Okay? So how do you explain this kind of behavior? The easiest explanation is that what's changing here, so we've pulled out the conversion kinetics piece, right? We're plotting all these other pieces that all experience conversion reactivities, and what we're really interested in here now is the nucleation rate and the growth rate. So at high temperature, when you make a large crystal, what does that say about what would the growth rate explanation for that be?
You're going to talk about what's changing, what's happening to the growth rate when you turn up the temperature that's consistent with these plots.
Yeah. All right.
Higher temperature and like at the graph, then the growth kinetics are going to go fast in the beginning, either less total particles, but then they get bigger.
Right. Exactly. Yeah. So if you keep the Sugimoto expression in mind, the number is inversely related to the growth rate. If the growth rate is faster, it takes fewer crystals to consume the solute.
Yeah.
Right? Growth rate is faster. Those crystals can consume solutes very effectively in any kind of competition, and nucleation is less important.
If the crystals stink at consuming solute, they go nucleate new ones. Right? So, interesting thing about these curves actually is that down here at 180 degrees, you can change the precursor conversion rate by a factor of 100.
And you don't really change the size at all. Okay? That's weird. Why would that be? It's because these crystals don't really grow very well. In fact, they hit the size of about 4.5 nanometers and they just quit. They stop growing. Unless you heat them up. If you heat them up, they'll continue to add solutes. Okay, so the interpretation of these plots is that if you want to grow a large crystal, you need some oomph. It's challenging to grow a large crystal. So that's our working hypothesis about this data. I'll show you another example of this in just a moment. It gets harder and harder to grow large crystals. Okay, you have to turn the temperature up by 100 degrees to get just a few nanometers larger.
Right? It's a big difference in temperature to get what seems to be a pretty small difference in terms of how big the crystal is. So this observation is consistent with the claim that you let the horses out of the game slowly, but the small ones grow more readily than the big ones do, right? That's consistent with the polydispersity being defined by the difficulty of growing a large crystal and the ease with which small crystals grow. So crystals naturally pile up in narrow polydispersity because of the fact that it's harder and harder to grow them the bigger they get. Now, eventually this stops because a micron-sized chunk and a 1.1 micron-sized chunk, they're identical. Surfaces are very similar. But down here in this very small scale, that's not true. Right? These are almost molecular. All right, so we're going to do one more example of this kind of thing. We're going to talk about Oswald ripening here. Remember, Oswald ripening is this sort of equilibrium process where some crystals dissolve and others grow. And that happens when the critical concentration is at the same size as the ensemble, okay, or basically at steady state. So when it's not supersaturated. Ice cream in the freezer will do this type of thing. And the reason it happens is that, you're supposed to be lowering the energy of the system by making a larger crystal. This is the driving force for growth. So we're going to look at an example of that in the synthesis of clusters. Okay. Clusters are this unusual situation where the surfaces are especially stable. You get particular geometries and whatnot. And we're going to look at an example of the Oswald ripening of clusters here. So, normally when you grow quantum dots, you can see evolution in size. You can tell the crystals apart. Few atoms shift the spectrum in a measurable way. You get the smooth evolution. But if you look down here at really small sizes, monitor at lower temperatures, you can actually make these little clusters where each of these excitonic transitions only appear at specific wavelengths. So if you look at this is a temporal evolution of crystal size. These are aliquots. And let's look at this peak here. In 15 minutes, you can see a crystal this big sort of growing in intensity, but then as the reaction progresses, it disappears. And as it's disappearing, the crystal is appearing and then disappearing. As a new crystal is appearing and then disappearing. This ensemble is jumping from one size to the next. And that jumping process is very slow and steady. And it says that there are only particular sizes that are stable here. You can't just add atoms willy-nilly. Only particular sizes appear. And the hotter you heat the reaction, it turns out, the longer this process can occur to larger and larger sizes. So what's happening here is an Oswald ripening experiment, and we went and made conditions where it was a lot easier to control that. We took this very reactive selenium compound here and mixed it with cadmium benzoate, this butylamine, but we've done this with a bunch of different aryl groups and amine ligands. Those guys react with each other to make cadmium selenide, and the cadmium selenide has cadmium benzoate and amine on its surface, and the formula you get depends on how big the crystal is. This compound makes a silyl ester byproduct. Silicon selenium bond is pretty weak, so that reaction happens readily even at minus 40 degrees. So you mix these two compounds together at minus 40 degrees, and this peaky looking thing here in red, spectrum of cadmium benzoate benzamine, gets replaced by a much stronger absorbance with time. You can see it growing in, and then if you warm that up to an ice bath, you can watch this stuff disappear and a new spectrum appear. And if you take that ice bath and then you let it warm up to room temperature, you can watch this spectrum disappear and a new spectrum appear. At room temperature, this sample gives us crystals that were used to obtain a single crystal X-ray structure of the type you see here. It's a pyramid of the zinc blende type of a structure. All of the surface atoms that you see here are green. Those are cadmium. It's a sleep on the inside. So this is a little chunk of the zinc blende X-ray structure that's cadmium terminated. Typical of crystal of clusters of this size, you don't see the ligands very well. We could have sort of modeled electron density, but I wasn't interested in trying to fart around with that because the data quality is not sufficient for my needs. And so we just said, hey, this is an indication that we're making these little pyramids. And it turns out that this process continues. If you keep the reaction, they get larger and larger, you make a series of different pyramids with formulas that you see here. So the interesting reaction, because all of the cadmium selenide in the synthesis is formed here at the beginning, and then you actually Ostwald ripen this cluster into that cluster. And if you heat the reaction up, that cluster will Ostwald ripen into the next size. Okay, and that process happens with isospecific points in the data. Okay, so when you have spectra that cross, you know, like this, where one species is converted into another species, if you really just have those two things in the flask and all of the material is conserved, the data will cross at these points called isospecific points. So when you see kinetics of this kind, it's a very good indication that you have one family of things turning into another family of things without any other variations going on and without the formation of intermediates. So, right? So what does that say about, we talked about this, I think. Jack, I'm sure remember we had a conversation about this, but we didn't discuss this in class yet, right? No. Sorry. So look at the formulas here. This guy is cadmium selenide 35. This one is cadmium selenide 56. This one is 21 cadmium benzoates, 42 amines. This one is 28 cadmium benzoates and 56 amines. They're spitting out all of this excess cadmium here. How the heck does this process happen? I mean, these are not integer multiples, right? There's no, you're adding layers, each of these pyramids. But in order for that to happen, a lot of rearranging has got to go on, right? You got to scramble one of these things to put it down as a layer.
So how do you Ostwald ripen so selectively like that?
We know these other ones. So here's the X-ray structure of cadmium selenide 350 that we obtained modeled against the PDF data. So here's the X-ray pair distribution function of this powder. The red one is the model. It's the calculated pattern on top of the experimental one. And the black gray wiggle down here is the data that we didn't capture with this model. Okay. And so for each of these different species we can pull out these reactions, we fit the X-ray PDF pattern very well with this little pyramid. We don't have crystal X-ray structures of these. We have PDF patterns of those. And we know we make them selectively because of this isospecific behavior. And so we know we have well-defined pyramids of this type. There are absorption spectra and their luminescence characteristics. I'm not going to get into the details of that. But you know, the amazing thing is that you get this selective production. Right? You're taking one cluster. This is the 305 cluster, which is smaller than the ones on this page. It turns into the 350. The 350 turns into 380. The 380 turns into 405. The 405 turns into 450, or whatever the number is. And you know, it has to happen by soluble matrices. Ostwald ripening must involve dissolution of one of these clusters into pieces. And when those pieces attach other clusters in the solution to grow the next largest size. Otherwise, I don't know how to explain the mechanism that you don't have integer multiples of units here that are converting. And the interesting thing about this reaction is that when you dissolve this one and break it into bits, those bits actually have a choice as to which crystal they're going to add to. So, you know, halfway through this conversion, you have a 50-50 mix of two liquids in the solution, right? And so when you make solubles, those solubles choose which cluster they're going to stick to. And they preferentially stick to the smaller one. If they also stuck to the larger one, that larger one will continue to grow, making it size. But it doesn't. Right? So only sticks to the smaller one, growing into the next size without sticking to that next size to make the even subsequently larger size. So this is another very clear example of smaller crystallites consuming solutes faster than large ones in an Oxford ripening experiment. So no nucleation at all. In fact, this is solution of particles with small ones faster than large ones do.
All right.
I think I'm out of time. But
For reasons beyond what we've talked about so far, we think that this suggests
an
energy information profile of something like this. As the crystals are larger, they become more stable, just like
some relationships
Yeah.
tests.
But we think the barrier
For forming them gets higher and higher. Okay, so
you start off down here, and the thing is getting to lower and lower energy, but it's harder and harder
you get there with time.
This kind of the fact the barrier goes up while the reaction becomes more driven is very
unusual.
generally speaking, when a reaction has a very dramatic force, it's thought
The
of
rate will be faster. Okay,
but the inverse
this is happening here.
and I think it's not a single way, but
It's a collection of many rates that are all working together.
so that gives, we think, this very unusual property where things tend to pile up and to get to larger sizes, you have to heat up.
Right.
Go from one pyramid
To the next, we had to heat it up.
So the take-home message here, I think, this stuff is, it's sort of down to the weeds
in a way.
It's detailed
And
complicated
to work through.
The thing
I
that
take home about this.
I hope you'll take home more, but the thing that your
Reflex should be
that it's hard to grow
crystals. Okay.
It's a barrier. There's like
It's a chemically challenging reaction.
and then, a lot of these crystals in the water are
Much higher temperatures than what we're growing them in solution.
So if
We're working down at very low temperatures in solution, it's possible to make little crystallites. And if you want to make a bigger crystal, you got to go up to the temperature at which the bulk is grown. Okay. So the higher and higher you go, the easier it is to make a bigger and bigger thing. And that's not the principle that you hear people talk about these systems with. You'll read the complete opposite when you look at papers. Okay, but this idea that temperature and size are related because of the difficulty of growing is a very important principle in this space, and something you should try and walk away with when looking at these materials and thinking about them. Okay, does anybody want, we're out of time, but if anybody wants to ask a question, happy to do that. Okay, I'll see you on Wednesday. Yeah. Yeah.
To both.